All right, this is our lecture number, I'm guessing 9. Okay, and in this lecture today we're going to discuss first topic in a big list of topics that we'll go over for the rest of the semester. And that topic comes from the area of statistics which is called inferential statistics. So, so far what we were doing in the previous lectures is, let's say we know the population distribution, can it be normal or some other form of distribution, or if we have the data set that we have collected, let's analyze this data set and let's create some summaries about the data set, such as, for example, plot the pictures, right? To see the visual representation of data, or calculate certain numerical things such as mean, mode, median, standard deviation, coefficient of variation, range, variance, interquartile range, first, second, third quartiles. So all of these things basically are fairly simple to calculate, to create, and they give you the insights into the data. So they summarize the data in a few numbers or just as a picture. A much bigger and much harder area of statistics is inferential. So in the inferential statistics, what we're doing is essentially testing a bunch of hypotheses or constructing confidence intervals. So we're going to discuss how we can use a sample in order to make conclusions about the population, which is a much bigger collection of data. So without further ado, let's get started. We're going to discuss two types of estimation. So this chapter, Inference about single population, deals with an estimations. Okay, so there are two types of inferences that we can do about the population as the whole. We can estimate the population parameters, such as mean of the population or the proportion if we're dealing with categorical data, or we can do the hypothesis testing. Well, hypothesis testing we're going to discuss probably, maybe not in the next lecture, but a lecture after that. So in this one we're going to discuss estimations. Just like I said, the estimation is a mechanism how we can use the sample in order to make conclusion about a bigger collection of data. Sample typically is very small compared to the population, right? So, for example, let's say you have 2 billion cars in the United States, and we want to estimate what's the average MPG for the population for all the cars in the United States. That is population. For that, we take 2,000 cars, measure their MPGs, and somehow from that conclude what the MPG might be for all the cars in the United States. So in this case, what we're doing really is we try to find out what's the population average, that would be mu, based on only a very small subset. So from the small subset we can compute sample average, and with all likelihood it's not going to be the same as the population mean, mu. So that's the goal for today. Okay, try to find out how we can use the sample in order to perform the analysis and get the idea of what the mu, population mean, can be, if the only thing that we have is the sample. Alright, so let's discuss the difference between the point estimator and the interval estimator. Point estimator is a very simple thing. I collect a sample, I calculate sample average, x bar, whatever that might be numerically, then I'm going to be simplistic and say this x bar is the mean of the population. End of story, I'm done. Well, easy to do, but unfortunately I'm not confident in this answer at all. Why not? In the previous lecture we have discussed sampling distribution, right? And sampling distribution is what? If I'm going to take possible samples out of my population, and for each sample calculate the mean, then each sample will give me different mean. Okay, and distribution of all possible sample means is what we call sampling distribution. And we discussed that sampling distribution, if n the sample size is large enough, more than 30, sampling distribution is going to be normal or approximately normal. A normal distribution is continuous, right? So for the continuous distribution, we know that whatever value of the random variable you can take, the probability to see exactly that value of this random variable is 0. Why is it 0? Because there are infinitely many, literally infinitely many different possible values of the random variable. So therefore, the chance to see exactly a certain one of them is, it will never happen, okay, because there are infinitely many possibilities. So since sampling distribution is approximately normal, that means that the chance that I'm going to get such sample, that x bar for this sample is going to be precisely equal, just by chance, to the population mean is 0. It's vanishingly small, okay? So therefore, as simple as it is to take sample, calculate the average, and claim that this is my population average, this is false, okay? In 100% of the cases, your true population average is going to be not the same as your sample average. So in order for you to have x bar exactly equal to the mean mu for the entire population, that has to be really, really lucky sample. Okay, so therefore, point estimators are easy to compute. Unfortunately, they're pretty useless. Okay, well, if they're useless, what can we do in order to be more confident? Well, to be more confident, statisticians came up with the following idea. How about we're going to not calculate one number, and that's why, by the way, it's called point estimator, because it's just one single number, but we're going to say, here's the range of different values, and we're confident that the certain percent confident that the true population mean is included somewhere inside this interval of values, okay? So therefore, it's kind of a trick, right, in a sense. We're saying that, well, we cannot know for sure what the population mean is. The only way how we can know the mu, the mean for the population, is if we get the entire population data, perform the calculations, and only then we will know 100% guaranteed what mu is. Well, that will never happen with all likelihood, so what's the next best thing? Next best thing is come up with a range and say, well, I don't know the exact value of mu, and I never will, but I am X% confident that it's somewhere between the lower limit right here and the upper limit. So in this chapter we're going to discuss how we can construct interval estimators for the population mean. And we discussed before that the calculations of the mean make sense only when you're dealing with numerical data. Data is categorical, such as nominal or ordinal. Numbers that you assign to different categories, they have no meaning. They're just for convenience purposes. So therefore, since these numbers can be changed, it's pretty much up to the statistician or analyst, right, which numbers to assign to different categories. That means that calculations of the mean don't make much sense. They don't bring much value, because numbers can be easily changed to something else. Okay, anyhow, let's keep going, right? So this slide summarizes what we just discussed. Point estimator is just sample average. We have zero confidence that this is the real answer. Population mean, with all likelihood, is going to be not the same as x bar. It's going to be something else, because all possible x bars have their own continuous distribution. Okay, so to claim that mean for the population is the same as the mean for the sample, we are not confident in this answer at all. With zero chance of that happening. Alright, so therefore, again we discussed that, right? What we're going to do is try to calculate lower boundary, which we'll call LCL, lower confidence limit, and upper confidence limit, such that in between these two numbers there is a X% chance that we have successfully captured the population mean mu. Okay. Alright, so now that's just a quick preview. So what we'll do in this lecture is we're going to take a look at analysis of the sample, and that would be numerical data. Okay, so therefore we're trying to estimate the population mean. In the next lecture, we're going to take a look at the case when the data is not numerical. Probably should replace that that word, not interval but numerical. Okay, when the data is not numerical but either nominal or ordinal, in other words categorical. And for categorical data, as we just discussed, we cannot really calculate any means, right, because of randomness of numbers. But we do have an option to calculate proportions, because nominal ordinal data is just a bunch of categories. For example, let's say we're going to look at the example with results of elections, voting, right? People voting, casting their votes for either Republican candidate or Democratic candidate. So there are two possible outcomes. How do we determine which one wins? Well, we calculate percentage or proportion of votes cast for Republican candidates, for example. And if this proportion is above 0.5, more than half people voted for the Republican candidate, then, well, that's it, Republican won. So therefore, for the categorical data, nominal or ordinal, we will not discuss population mean, but instead of that we'll discuss population proportion. Okay. Now, let me actually go back to... No, yeah, that's right. Problem with estimation of population mean is that we don't really know neither population mean itself nor the standard deviation of the distribution for the entire population. So the only thing that we have at our disposal really is a sample, right? It's kind of flying blind situation. We collect a sample, can be a big sample, doesn't really matter. The point here is that the sample is still much smaller than the entire population. It's just a fraction of all possible data points, right? And we don't know anything about the population. We don't know the mean and we don't know the standard deviation. So our best guesses about what the mean can be and what sigma can be is what we can calculate from the sample. From sample we can compute sample mean, x bar, and also standard deviation, s. And it's not going to be the same as sigma, right? Just like x bar is not the same as mu, s is not the same as sigma. Things that we compute from sample are different from what they actually are if we had access for the 100% of the data points about certain subject matter. So when we discussed in the previous lecture sampling distribution, we mentioned that if you take variable x, whatever it is normally distributed, subtract the mean for the distribution and divide by the standard deviation, you will get a z, right? It's a standardized, it's a standard normal distribution, something that's distributed according to standard normal distribution. While statisticians shown that if you take potential all possible x bars, sample averages, subtract the true mean of the population, which still remains unknown, right, and divide by the estimate for the standard deviation, and that would be s over the square root from n, then you'll get something which is not exactly distributed like z, standard normal, but is distributed as t. T is sometimes called students distribution or t distribution as well. The reason why, here is the formula for ugly looking formula for the t distribution, right? Which you don't need to memorize. Okay, so let me give you kind of a little bit of funny story why this distribution is called students. First one who proposed the distribution, the t distribution, was a statistician who worked for Guinness, for the beer company, and he was just interested in statistics. So he was doing some calculations about quality of the beer that they were making. He wanted to publish that, but company policy was that this is private information, so you can't publish that under your actual name. So he published that under the kind of pen name, pseudonym. He signed his papers as student, and the t-distribution was introduced in these papers. So since then, t-distribution is also called student distribution. Okay, so student distribution actually looks a lot like standard normal. If you remember our discussion of standard normal, the average for the standard normal is 0, and the standard deviation for the standard normal is 1. Now, student distribution, so therefore we also have discussed that in order to fully specify normal distribution shape, you have to provide two numbers. First is mean, the location of the peak, and the second is standard deviation, how wide is your distribution to the right and to the left. Two parameters we need for the normal distribution. I'm going to the previous slide. For the t-distribution, we need only one parameter, and that parameter is called number of degrees of freedom. Okay, so for all intents and purposes that we're going to use t-distribution, that's something that you need to memorize. Number of degrees of freedom is equal to sample size minus 1. So if I collect a sample with 100 observations, and I have to use t-distribution with 99 degrees of freedom. If I have 500 observations, it should be 499 degrees of freedom. So difference between t-distribution and normal is that for normal we need two parameters, mean and standard deviation. For the t, we need only one, number of degrees of freedom. Okay, so what makes t-distributions look so similar to the standard normal? Well, first of all, it's unimodal and ball-shaped, so therefore there is only one peak, and it quickly goes to 0. It's symmetric, quickly goes to 0 on both right side and the left side. The variance or square of the standard deviation, for normal distribution the variance is 1 and the standard deviation is 1 for the standard normal, right? Now for the student distribution, it's not. So the variance is given by this ratio, degrees of freedom divided by the degrees of freedom minus 2. But look what happens. We just discussed that number of degrees of freedom is sample size minus 1, right? So let's say I'm taking samples with 100 observations. So in the numerator I have number of degrees of freedom 99, that's 100 minus 1, right? In the denominator I have 99 minus 2, that's 97. 99 divided by 97 is number close to 1, slightly higher, right? What if I get bigger sample? Instead of 100 observations, 1,000 observations. Well, in the denominator I have 999, in the numerator 997. The ratio is also very close to 1, and it's smaller than for the sample of 100. If I take 1,000,000, really big sample, right? That's 999,999 in the numerator and 999,997 in the denominator. Almost exactly 1.0, right? So the point of the story is this. As we keep taking bigger and bigger and bigger samples, the variance for my student distribution is getting closer and closer and closer to 1, and the same is true about the standard deviation. The bigger the sample, the closer standard deviation to 1. So in other words, as I take bigger and bigger and bigger sample, my t-distribution will start approach standard normal, closer and closer and closer. So I don't find this picture very nice illustration. So you can see that as you change the shape, as you change the sample size, right? So here is 2 degrees of freedom. Can't even, yeah. So lowest curve is the 2 degrees of freedom. Okay. Then you increase that sample size to 11, so the degrees of freedom is 10. Then it becomes more pointy, so to speak, right? Then 30 degrees, 30 degrees of freedom. Then it becomes even more pointy, right? So the point here is that as you start getting bigger and bigger and bigger sample, the shape of the student t-distribution is becoming closer and closer to standard normal, z distribution. Okay. So since we don't know anything about our population, that's exactly what we're going to use. Okay, so if we knew sigma, if somehow, and how can you know sigma, right? You don't know anything about the population. You don't know true mean, and you don't know true standard deviation. But suppose somehow we figured out the sigma, but still don't know the mean mu. In this case, sigma is known, and x minus the actual mu divided by sigma over square root of n, that would be the standard deviation for the sampling distribution, will give us the z distribution, right? Something that's distributed with z as z random variable. But we don't know sigma. So we use the next best thing, that would be s, population, sample standard deviation, right? So if we replace in this formula sigma with s, then the result is going to be t distributed with n minus 1 degrees of freedom. So df, this symbol right here, subscript, n minus 1 degrees of freedom. Okay, and so how do we estimate how do we estimate the mean mu for the population? It's very simple, really. Okay, and you will see. We'll take a look at that in just a couple of minutes for a certain specific practical problem. But the value t right here in this formula essentially gives you how many standard deviations do you have to go up from the x bar, from the sample mean, or down from x bar in order to calculate these two values, lower confidence limit and upper confidence limit. And you can imagine that the value of t, number of standard deviations away from x bar, will depend on how confident we'd like to be. Okay, if we'd like to be 0% confident, means that you don't have to go anywhere really. So x bar is your point estimate, but you have no confidence in that, so therefore your confidence interval really becomes 1 point with 0 confidence in that, right? The more confident you are, the higher the t value, okay? Because that will drive up the width of the confidence interval. If you want to be highly confident, your confidence interval will be really wide, okay? So it will include a lot of different possibilities. Well, you will see in just 1 second. Okay, I have a nice illustration for you. All right. So first things first, we want to pick confidence level. Let's say it can be 90%, and in statistics there are certain standard values for the level of confidence, just like for the level of significance, which we didn't discuss yet, but we will in the nearest future. Okay, so let's say we want to estimate our population mean with a confidence of 90%. That's something that's called confidence level. So that means that in 90% of the cases, the confidence interval that we will construct will include the population mean, right? So every single confidence interval that we construct, there is a 90% probability that this confidence interval will include the true population mean somewhere inside of that. And there is 90% chance that it will not include. Okay, so my CI confidence interval is going to be either on the high side or on the low side. Okay, so that means that we have to include 100 minus 90, that's 10%, divided by 2 in each tail of the distribution. So 5%, 0.05, and minus point in the right tail of the distribution, and the same 0.05 in the left tail of the distribution. So every once in a while, our sample mean x bar will be on high end or on the low end, sufficiently far enough from the true population mean, such that our confidence interval will fail to capture the population mean mu. Okay, so the first step that we have to do for construction of the confidence interval is come up with confidence level and then find two different values. Positive t, that cuts off, well, in that case 90%, so 100 minus 90 divided by 2, 5%, 0.05 area in the right tail of the distribution, and the symmetric one, minus t 0.05, that cuts off exactly the same area, 0.05 in the left tail of the distribution. Why do we do that? Because as you can see, the average for all the t distributions, no matter the degrees of freedom, the average is always 0, so it's symmetric. So if I have t value right here that cuts off 5% on the right tail, I take minus that value on the other end, and it will cut off exactly same value, exactly same area, 0.05, in the left tail of the distribution. Okay, so because of symmetry, I have to take the same value but with different signs, plus and minus. Okay. All right. So the next step, once we found the value of t that we need to use, is to construct something that's called margin of error. Okay, but other different values that are being used for the confidence. So here we discuss the confidence level, right? How confident we want to be in our results. So, and I told you that 90% is one of the standard values for the confidence level, right? So I want to be 90% confident that whatever upper and lower confident limits I constructed, somewhere between them, I captured the true population mean. That's one of the standard values. Another standard value that is used to construct confidence interval is 95%. In fact, this is pretty popular way to choose the confidence level. And unless something opposite, something different is specified by default, confidence level is assumed to be 95%. Another, if we have 95% confidence, that means that 100 minus 95 gives you 5%, and again we have to split that between the right tail and the left tail of the distribution, which means that in each of the tails we have to have 0.05 or 5% divided by 2, or 0.025, right? So in this case we're looking at t 0.025, 2.5% on the right tail, or minus t 0.025, same 2.5% on the left tail of the distribution. And yet another way how confidence interval, confidence level is oftentimes selected is 99%. But that's considered to be pretty strong confidence level. Okay, so standard values are 90% or 95, which is usually used, or 99%. Okay, so here actually what I did is I found on the internet a pretty cool illustration of what confidence interval really is all about. Okay, so let's go ahead and take a look at this demonstration. All right, so here I can pick different parameters and play around with them. So I'm going to try and capture the population mean. So I believe somewhere here, yeah, right here, I can set up my population mean to be anything. Let's say my population, the true population mean, the actual, factual, big, fat, uncatchable true population mean is going to be 10. Okay, so I'm going to hit enter, and there it is. And let's say that my population standard deviation sigma is, I don't know, 2. Bam. Okay, so here's what I'm going to do. I am going to start with 90% confidence level. Okay, 90%, and each time when I am going to here I'm going to simulate samples, right? So this is a simulation actually. So this one takes out of normally distributed, I believe it's normally distributed, yeah, this app randomly generates samples of n. In our case n is 4, right? Each time when we get a sample, it's 4 items. Okay, and they come from a normal distribution. Normal we just set up mean of 10 and sigma 2. Okay, so it looks like bell-shaped with a peak around 10. Okay, and then it quickly goes to 0 on the right and on the left side. That's how population is distributed. And we're getting 4 items out of this normally distributed data, and then calculate sample average and construct the confidence interval. So what you see here really is, here's my first sample. Okay, was the average. I don't know what it was really numerical, but it looks like around 11, right? First sample had 11-ish, the average, and we constructed a confidence interval, 90% confidence interval, and these two lines, they represent, here's my lower limit, here's my upper limit. And you can see that here's the mean, right? The idea behind confidence interval, once again, is to try and capture the actual mean mu within my confidence interval. The mean doesn't go anywhere, okay? The mean doesn't jump around. Mean is 10, done. That's it. Population mean is 10, right? What I'm trying to do is I'm trying to construct the confidence interval CI such that in between these boundaries, lower and upper limit, somewhere inside my confidence interval, I'm going to capture the mean. And I can see that my first sample captured the mean accurately, right? It's right here. It's inside between my lower and upper confidence limits. My second sample has X bar around 9, I'm guessing. And once again, it did capture the mean mu 10 inside of that, right? So it's between lower and upper confidence limit. Same happened with my third sample. You see what's happening? I'm picking different samples, right? Samples give me different averages, right? And what happens is, from the average for the sample, I always go up a certain amount and the same amount down. That's how I construct my upper and lower confidence limits. And if I captured the mean inside, that's a success. Okay, that's good. So let's see what happens if I pick, instead of 5, 100. So here are 100 lines, 100 different samples, and you can see these circles right there. They represent sample averages. They're all over the place, right? And almost none of them you can see that are spot on at 10, right? That basically illustrates one more time the point that my X bar will pretty much always be not the same as the mean mu for the population. It will be all over the place. Most of them will concentrate around 10. Yeah, that's given. Okay, but some of them will be so far away that even if I construct a 90% confidence interval, it will not include the population mean. And they're represented here as red confidence intervals, right? So this one, for example, see that? My upper limit is short, a little bit short of the actual population mean. Here my lower limit is pretty far away, right? Here it's also away. So how many of them do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, 90% confidence level basically means what? If I generate 100 samples, on average, 10 out of these samples will not capture my true population mean, right? So let me go ahead and resample. I'm going to get another sample of 100 different, another set of 100 different samples. So in the previous one, I believe 9 didn't capture, right? And on average, I'm supposed to see 10. So what do we have now? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, right? 14 samples didn't capture the mean. And I resample again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. I resample again. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's clearly more than 10. That's less than 10, probably. 1, 2, 3, 4, 5, 6, 7, 8, 9. Now that's 10, exactly. That's also close to 10. So you get the idea, right? Every time when I calculate 100 different samples, number of samples, number of confidence intervals that are too far away from the mean changes, right? Sometimes I have 9, sometimes I have what's here, have 7, right? 1, 2, 3, 4, 5, no, even 6, even less than that. Sometimes I have get 9, sometimes 12, but on average, 10 will not get my mean mu, and 90 will get my mean mu. All right, let me go ahead and see what happens if I change my confidence level to a different value. Remember, we discussed 90 is standard, 95 is also fairly standard. Okay, so what happened is, let me see if we can actually spot what happens visually. So here's my 90, and here is my 95. You can probably see how confidence intervals become more wide, right? As I increase my confidence level, each one of my confidence intervals becomes more wide. That's what happens. Okay, if I want to be more confident, that my confidence intervals include the true population mean, that means that I have to include bigger range for my confidence interval, right? And there is a bigger chance that it will catch the population mean mu. And that's what happens. If your confidence level goes up, the width of your confidence intervals also goes down, goes up, right? So here, I'm supposed to get 95% on average of all the confidence intervals to catch my mean mu, which is 10, and about 5 on average will not do that, right? So here, out of 100, 1, 2, 3, 4, 5, 6 didn't catch, right? Resample. Here I have only 1. Everybody else caught the mean mu 10. Here I have, oh my god, a bunch. 1, 2, 3, 4, 5, 6, 7, 8, 9, right? And I resample again 3 only. Resample again 2. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So as I pick different set of 100 samples, the number of the ones that I missed, right? Number of CIs that are missing the mean mu, it goes up and down, so it's a random number by itself. But on average it stays around 95, right? And let's change it to a different one, right? 99%. And you can see that now my confidence intervals, they're really wide, right? Again, you increase the confidence level, the interval becomes wider, because then it will more likely capture the mean, right? So in this case, out of 100 samples, on average 99 will include the mean and 1 will miss. So in this case, I missed 3 times, right, out of 100. Here, everything, right, every single one of them included the mean mu. Here I have 3 again, here I have 2, here I have 3, 1, 0, 0, 0 again, 0, 2. So you can see that it pretty much holds true, right? If I keep clicking all day long, then I will get probably on average that there is 1 out of all these 100 samples, there is on average 1 that did not capture the population mean 10, and 99 that did capture. Okay, so let me go back to 90, and you will see that the confidence intervals shrink, right? What happens if I increase the sample size? Okay, so this is another thing that we can change in order to see what's happening, right? Sample size, right now it's 4. What if I increase the sample size to 16? Why 16? It's a nice number. Square root of 16 is 4, right? You can visually see what happens, right? So it used to be 4. For 4, it was pretty wide. But if I get a bigger sample, 16, it becomes more narrow. So the larger the sample size, the more narrow are my confidence intervals, right? Next one is 25, right? Because 20 square root from 25 is 5. You can see that it becomes even more narrow. How about I have 100? They become really narrow, right? But still the same rule applies, okay? Since I'm using confidence level of 90, right now, on average, 10 of these 100 samples will miss the mean mu 10, the mean of 10, right? And 90 will include the mean of 10. So if I resample, I can see that the number fluctuates, right? But it kind of stays around 10-ish. Okay, so that was kind of a nice illustration, I thought. Alright, let's go back to the lecture, okay? Let's give it a practical spin, okay? And I will illustrate exactly how the confidence interval is created. Well, first of all, I want to point out that confidence interval is built around x bar, sample mean, okay? So, sample mean, x bar, is always in the middle of the confidence interval. Simple as that. FedEx. So, business related problem. FedEx, company that moves packages, right, would like to reduce the cost, and that's what they actually do, okay? They hire and fire workers to meet the demand. So during the normal year, not like 2020, when you know, the economy is kind of working as opposed to what it's doing right now, FedEx is a seasonal company, okay? They see peak demand right around probably end of the year, and the rest of the year it's pretty much business as usual for them. So how do they meet the peak demand? They hire temporary workers, and they like to rely on students actually to go and work in the sorting facilities to sort the packages. So an average experienced worker can process 500 packages per hour on average. What they do is they hire new people they put them through the training program, and they expect them within 1 week of being hired and trained to be able to achieve not quite 500 but close, 450 packages per hour on average. Big fat question: are they effective? Is their training program meeting the stated goal to achieve at least 450 packages per hour or more productivity after hiring fresh people and training them for 1 week? Is that what happens, or do they fall short? Well, let's see. Again, sampling, right? How can we find out if on average newly hired people after 1 week of training do 450 packages per hour? We can't possibly track every single one of them, right? It's just too much data collection. So therefore, they settle for, not surprisingly, a sample. So they take 50 workers, put them through 1 week training program, and after that they ask every single one of them, hey, can we go ahead and do the package sorting, and we'll just track you, okay, for 1 hour. How many packages you will finish within 1 hour time. So we have recorded 50 different numbers, right? So they are supposed to be in the file fedex.csv. So, and the file is posted on Scholar, so you can download the file from Scholar. But before we do that, let me point out one very important thing. At the end of this semester, we're going to discuss something that's called non-parametric statistics. Non-parametric basically means that there are no parameters, right? So all these things that we talked about in numerical descriptive techniques, mean, mode, median, they don't make much sense anymore. Well, with the exception of the median, probably. Median still makes sense. But mean, if you have some weird looking distribution, bimodal for example, okay, or trimodal, it's even worse, okay, then the whole idea of the mean, it kind of disappears. Mean doesn't measure anything anymore because your distribution just looks weird. That's it. It's not the center of the data. Your data, if anything, it has many different centers now, okay? So therefore, every time when we discuss estimation of the mean, we basically need to require that your data behaves nicely. And what that means is it's normally distributed or close to normally distributed. When it's extremely non-normal, such as very much skewed on the right or highly skewed on the left, or it has 2 big peaks or 3 different big peaks, just doesn't look like bell-shaped distribution at all. This test does not apply. So therefore, before we proceed, we have to check data for normality. For now, we're going to just look at the histogram, okay? If my population is normally distributed, and I take random sample, I can expect random sample to be also normally distributed, right? Because sample gives me kind of a little picture of the population, right? So for now, we're going to test normality by just visually looking at the histogram. In the next few lectures, we're going to discuss hypothesis testing, and from that point on, we're going to actually use rigorous statistical test in order to see if the data is normal or not. It's called, oh god, what's it? Forgot what the name of the test. Just had it in my mind, just slipped in my mind. Wilk test, right? I believe we're going to use the Wilk test for that. Yeah. All right. So let's go ahead and do the analysis. So I'm going to exit from PowerPoints and bring in the RStudio. Okay. So here's my RStudio, blank. So I'm going to create a new R script, and of course, just like we always do, first things first, we have to download the data from Scholar, move it to the folder C, disk C folder data. I did that already, so you need to do the same thing. And I'm just going to do the analysis right now. So first things first, read data from CSV file, just like what we always do, right? So I'm going to call it FedEx data. Okay, and this is read.csv, quote unquote, disk C, folder data, and it's called fedex.csv. CSV. Bam. Okay, so the data is in, and now, very important step, check if histogram is normal, and we can use confidence interval, right? Confidence interval to estimate population mean. All right. So if you remember, the way how we do histograms is HIST, and let's see. Probably inside my data FedEx, I have only one column. That's what I'm guessing, because there is nothing else, right? Just 50 numbers. Each number tells me how many packages that specific individual processed per 1 hour. That's it. So FedEx data $, and indeed I have only one column, packages, number of packages, right? Okay, so this is a quick and dirty plot. What do I see? Is it normal? Well, it's not the most normal, most perfect normal data, but it's not too bad, right? Overall, it does follow the unimodal bell-shaped form, right? Maybe there is some skew, but hey, this is a sample. What can you expect from the sample, right? That's the best that we can get. Okay, so I can proceed. Let me go back to the slides. So here is how, and yeah, on this slide I do exactly that actually. Test the shape, right? So here is what we need to do. In order to construct the confidence interval, first of all, we have to construct the X bar, sample average. So, and that's going to be the center of my confidence interval, right? Remember, in the middle of my confidence interval, always I have sample mean, okay? So, sample mean, and I'm going to call it X bar, X underscore bar, because that's what I use in order to denote the sample mean, right? If you remember, it's very simple, using mean, right, function, and that would be FedEx data, $, and packages is the column that I'm using. Okay, so I calculate the mean, X bar, so let me go ahead and see what is X bar. X bar says, on average, these 50 gentlemen / ladies, right, that I hired and trained for a week, on average, they achieve the productivity of 454 packages. So, mission accomplished, right? My goal was 450 on average. I got a sample, and the sample says 454. It's more than 450, so therefore my training program is a smashing success. Well, how confident am I that 454 is the actual value of the population mean? So if I take a look at all the workers that I train, at all the hours that they work, and calculate the mean productivity, it's going to be 450 or more. The confidence in that answer is 0, right? Whatever the actual productivity is, it's not going to be 454. We discussed that, right? This is just a point estimate. There is 0 chance that this is my actual population mean, right? So let's turn our attention back to the slides. How do we construct the confidence interval? Well, first things first. In order to construct the upper and lower confidence limits, I have to go up from X bar, certain amount, and down from X bar. That gives me upper and lower confidence limit. How much? Here is the formula, okay? Again, T gives me the number of degrees of freedom. Oh, sorry. Number of standard deviations, right, that I have to go to the right and to the left. S is something that I need to compute. That's just a standard deviation of the sample. And I need a square root of n, and this is the formula, right? Number of standard deviations times S divided by the square root from n. Okay, well, let's get cracking. I'm gonna bring back the our studio. So first things first, right? Let's calculate sample standard deviation. Deviation S, right? That's what we use for sample standard deviation. So S is, if you remember, it's the function SD, and again same date, right? FedEx $, packages. Alright, so it's done. It's computed. I don't really care about the value, quite frankly. I mean, If it's big, if it's small, how do I use it? Well, I have to calculate margin of error, right? And S is the part of the calculation. That's all there is to it. And the next one is N, right? So I'm going to calculate sample size, okay? And if you remember, N, little n is the letter that we use for that. How do I calculate sample size? It's just simply number of records in my data set, right? That's it. So I told you that I can find out how many records by just running the function n row, number of rows. Same thing, right? FedEx data $ packages. Okay, so it gives me a number of observations, and I believe the problem stated actually that it's 50, right? 50 workers. Let's see. Whoopsie. FedEx data. Okay, yeah. So it's not just packages; it's in the entire data set. Okay. So n is 50 workers. It's a good thing that I run this line, right? Without that, it would give me a bad error at the end. Okay, so I'm actually almost there, right? So I got an S, sample standard deviation. I got the number of degrees, sample size, so I can calculate square root from n. The only thing missing is I need a t, right? How many standard deviations I have to go from x bar to the right and to the left. So what do we pick? What level of confidence do we pick? Do we pick 90%, 95, 99? Which one? Well, this time around, I propose that we go with the standard, right? By default, 95 confidence interval. Okay, so literally what I'm going to do is, well, let me switch back to our studio, right? So now I need to calculate t value. All right, well, first things first, right? How many, let me actually go ahead and do this. I'm gonna say confidence that I'm going to use is 95%, right? It's 0.95, and I'm going to run this line. It's not effective. It's not really, didn't happen unless you ran it, right? Okay, so I'm going to be 95% confident, right? So therefore, the area that I need in the right tail and in the left tail together is 5%. Divided by 5, that gives me 0.025, right? All right. How many degrees of freedom do I use? Remember our discussion some time ago, just recently. Number of degrees of freedom to use is always sample size minus 1, right? So therefore, with n minus 1 equals, and we know that n is 50, right? 49 degrees of freedom. Degrees of freedom. Okay. Freedom. That gives 0.025, right? It's 5% divided by 2, evenly split between right and left tail, in the right tail of t distribution. This is quite literally what I'm looking for, right? Now for that we're going to use a new function. Remember how we calculated the value for the area or for the probability in case of normal distribution? We use the function qnorm, right? Pnorm gives us probability for a given value. Qnorm gives us value for a given probability. Same exact thing applies to the t distribution. So I can calculate pt, probability for the t distribution, or I can calculate qt, quantile or quantity for the t distribution. And that's exactly what I'm looking for, right? So and here, by the way, is the description, right, of what exactly the function will take. First it will take the area itself, p, probability. Then next one, disappeared. Next one is number of degrees of freedom. That's the only parameter that I have to send to specify fully the function t distribution, right? And after that, same thing as what we did for the qnorm or pnorm. Lower tail, either true or false. Okay, well, let's get down to it, right? First things first, probability in the tail. Well, it's 0.05 divided by 2, but I can do it like this, okay? I can go ahead and say 1 minus confidence. minus confidence, right? Oh, here I screwed up, right? Confidence. Okay, run it again. 1 minus confidence. Come on. I hope I didn't misspell it this time around. Confidence, and divided by 2, right? 1 minus confidence gives me the total area in the right and the left tail, divided by 2. That is my probability, right? Second one is df, degrees of freedom. df is, well, I know it's 49, but instead of that I'm going to say n minus 1, right? Because I already know what's n. I recorded it right here, number of records in the cell, right? And the last one, where am I looking, in the right tail or the left tail? Well, right tail. So lower tail equals false. Upper tail equals true. And by the way, I need to record it somewhere, right? Because if it will execute, I mean, it will sit in the memory, but there is no name to that, right? So how do I call it? I'm going to call it t-value. How about that? I'm going to call it t-value. All right, let's run it. And let's see what t-value did we calculate. T-value is right here, 2.095. Tells me that the value for the t-distribution, that gives me 0.025. That is 0.025 in the right tail. Lower tail is false. For the degrees of freedom, n minus 149 is right here, 2.0095, right? Well, and I have all components in place pretty much. So now I can compute my where is the formula? Right here. Margin of error. It's t-value times s divided by the square root from n. And I'm going to quite literally do that, okay? So here I'm going to put a comment and say compute margin of error, okay? And I'm going to call it ME, margin of error, equals t-value, right, that I just computed, multiplied by s. That's what I called my standard deviation right here, okay? And after that also divide that thing by square root, sqrt, from n. And n is also, well, I have the n, right, sample size. Kaboom. Okay, so let's see how much is margin of error. 9.4, right? So after that I can compute my upper confidence limit and lower confidence limit, like this. So upper confidence limit is my x bar plus margin of error, right? So I go margin of error above x bar and below x bar. So x bar is always in the middle of my confidence interval, right? And lower confidence limit is x bar minus margin of error. And let me run both of these lines. First one, second one. And now let me show them, right? UCL right there and my LCL right there. Okay, so what do I see? Well, here's the result. Okay, if I want to be 95% sure, right, I use 95% confidence limit about where exactly is my true average hourly productivity for freshly hired and trained workers, then it's somewhere between 445.1 packages per hour to 463.9 packages per hour, okay? And remember when we discussed what can we calculate from x bar, right? What can we conclude? X bar was 454. It was above 450, and my goal was 450 or better. That qualifies as 450 or better, right? So just based on x bar, I would say, yep, it's beautiful, my program is working. They do achieve average productivity. Problem is, this is just sample average, a point estimate. Now that I get more confident, right, I have upper and lower confidence limit. And am I so sure right now? Well, you can notice that my lower confidence limit is 445, it's below 450, right? So part of my confidence interval is above 450, and another part is below. So based on this confidence interval, I cannot really conclude that my true productivity is higher than 450 packages per hour. Could be less than that. And the reason is exactly right here, okay, because sum of my confidence interval is under 450. So the true productivity can be below 450 or above 450. There is no way to tell from this sample. Do you see how statistics is tricky, right? What seemed to be a sure thing, done deal, based on the X bar, I'm not so sure anymore when I'm looking at the confidence interval. Right? It doesn't give me such a clear-cut answer. I don't know. Can be below 450 or above 450, right? So the answer to the question originally posted in the problem is that true that they achieve productivity of 450 or higher? The answer is this. Based on this sample, I cannot claim that really. Okay, 95% sure that it's somewhere between 445 and 463.9. Could be below. So based on this sample, I cannot support that claim. Okay, that they do truly achieve 450 packages per hour or more. Okay, and that's the end of our lecture. I believe it went slightly over time limit. Oh, actually, yeah, it's 1 hour. In the next lecture, we're going to take a look at slightly different, similar but different problem when we're dealing with not numerical but categorical data.